What if the future of quantum computing doesn't belong to the biggest names you hear about most often? What if the platform that could one day transform drug discovery, materials science, logistics, finance, and even artificial intelligence isn't the one running at near absolute zero inside giant refrigerators, but one built from individual atoms held in place by beams of light? That's not science fiction. It's called neutral atom quantum computing. And right now, it's becoming one of the most serious contenders in the global quantum race. And in this video, we're breaking it all down: what neutral atom quantum computing actually is, why scientists and investors are paying close attention, how it compares to superconducting, trapped ion, photonic, and topological systems, and whether it could really become one of the leading platforms for practical quantum computing. By the end, you'll understand not just the science, but the strategy. Let's get into it. Quantum computing is one of the most important technological races of the 21st century. Why? Because classical computers, as powerful as they are, eventually hit limits. Some problems become too complex, too massive, or too interconnected to solve efficiently with ordinary machines. Quantum computers promise a different path. Instead of using bits that are either 0 or 1, they use qubits, which can exist in combinations of both at once. That unlocks new ways of processing information using superposition, entanglement, and interference. But here's the catch. There isn't just one type of quantum computer. There are multiple competing platforms: superconducting qubits, trapped ions, photonics, topological ideas, and neutral atoms. And each one comes with trade-offs. Neutral atoms are especially exciting because they seem to sit in a very interesting middle ground, not the fastest, not yet the most mature, but potentially one of the most scalable and flexible. So what exactly is neutral atom quantum computing? At its core, it means using individual neutral atoms, often atoms like rubidium, cesium, ytterbium, or strontium, as qubits. These atoms are trapped and arranged using highly focused laser beams called optical tweezers. Think of optical tweezers like invisible laser fingers that can grab and hold single atoms in space. Once the atoms are trapped, scientists can manipulate their quantum states using lasers or microwave fields. Those internal atomic states become the zeros and ones, or more accurately, the quantum versions of them. Now here's where it gets really powerful. These atoms can be excited into something called Rydberg states. In those highly excited states, atoms interact very strongly with nearby atoms. That interaction allows researchers to perform 2-qubit gates, which are essential for creating entanglement and doing real quantum computation. So in simple terms, the atom is the qubit, the laser holds it in place, other lasers control it, and Rydberg interactions let qubits talk to each other. That combination is a huge reason neutral atoms have become such a serious platform. The report highlights several reasons neutral atoms stand out. 1. Scalability. Neutral atoms can be arranged in flexible 2D and even 3D arrays, and scientists can often rearrange them dynamically. That means this platform has a very strong path toward larger systems. Current systems already range from around 100 to 300 operational qubits, and some demonstrations have reached 1,000 qubits, with roadmaps aiming much higher. 2. Long coherence times. Coherence time is basically how long quantum information survives before noise destroys it. Ground-state neutral atom qubits can maintain coherence for seconds, which is extremely impressive compared with some other platforms. 3. Flexible connectivity. Because atoms can be rearranged and because Rydberg interactions can span multiple micrometers, neutral atoms can sometimes support more flexible connectivity than platforms stuck with fixed chip layouts. 4. Lower infrastructure burden. Unlike superconducting systems that need dilution refrigerators operating around 10 to 20 millikelvin, neutral atom systems can operate at room temperature or with more modest cooling. That could mean lower infrastructure costs and greater deployment flexibility. 5. Naturally identical qubits. Atoms are atoms. They don't suffer from the same fabrication variability you get in manufactured circuits. That natural uniformity is a real advantage. So if you step back, the pitch is clear. Neutral atoms offer a compelling mix of scale, coherence, flexibility, and physical elegance. Of course, no platform is perfect, and the report is very clear about the weaknesses too. 1. Gate speed. This is one of the biggest limitations. Neutral atom 2-qubit gate times are typically in the 1 to 10 microsecond range. That is much slower than superconducting qubits, which often operate in the 10 to 100 nanosecond range. That means superconducting systems can often perform many more operations in a short window. 2. 2-qubit fidelity. Neutral atom systems have made impressive progress, with reported 2-qubit fidelities in roughly the 97% to 99.7% range, and notable results like 99.4% controlled Z fidelity in Ytterbium-171 systems. But the platform is still pushing toward the ultra-high fidelity thresholds needed for highly efficient, fault-tolerant quantum computing. 3. Atom loss. Atoms can be lost during computation due to collisions or other disturbances. That becomes a serious concern for long and complicated computations. 4. Measurement challenges. Reading qubits out, especially non-destructively, is hard. Fluorescence detection can achieve high fidelity, but measurement times are slower than in some competing systems, and non-destructive measurement is still an active development area. 5. Engineering complexity. Even though neutral atoms avoid extreme cryogenics, they still require sophisticated laser systems, precise optics, high vacuum chambers, control electronics, and careful calibration. So this is not easy hardware. It is just a different kind of hard. That's an important point. Neutral atoms are promising not because they remove all the challenges, but because the challenges they have may be more manageable at large scale. To understand where neutral atoms fit, you really have to compare them with the rest of the field. Neutral atoms versus superconducting qubits. Superconducting systems, used by companies like IBM and Google, are currently among the most mature and fastest. Their gates are much faster and their ecosystems are more developed, but they need extreme cryogenic cooling and they face challenges in coherence and fabrication uniformity. Neutral atoms trade speed for coherence, flexibility, and potentially lower infrastructure burden. Neutral atoms versus trapped ions. Trapped ions are famous for very high fidelities and long coherence times, but they tend to be harder to scale to very large numbers because of motional mode complexity and trap engineering challenges. Neutral atoms may scale more naturally to larger arrays, even if trapped ions still often lead on raw fidelity. Neutral atoms versus photonics. Photonic quantum computing has huge strengths in networking and room temperature operation, but photons are harder to make interact deterministically. Neutral atoms, by contrast, can produce strong interqubit interactions through Rydberg blockade, which makes entangling gates more straightforward in many cases. Neutral atoms versus topological qubits. Topological qubits are exciting in theory because they promise built-in error resistance, but in practice they remain far less mature. The report makes it clear that neutral atoms are commercially active today, while topological systems remain much more speculative. So where do neutral atoms sit? They're kind of the balanced contender, not always best at any one metric, but very strong across several of the ones that may matter most for long-term scaling. This is where the story gets even more interesting. Neutral atom quantum computing isn't just a physics experiment anymore. It's becoming a business race. The report points to several major players: QuEra Computing in the US, with investment and strategic connection to Google; Atom Computing, which is partnered with Microsoft Azure Quantum; and Pasqal in France, which reportedly achieved 1,000 qubits in 2024 and has laid out aggressive scaling goals. That matters because cloud integration changes everything. Instead of every university, company, or government lab needing to buy a quantum computer, it can access one remotely through cloud platforms. That lowers the barrier to entry, speeds up experimentation, and builds an ecosystem around software, applications, and hybrid classical quantum workflows. The report estimates the neutral atom sector's current revenue around $50 million to $100 million in 2026, with long-term projections ranging much higher depending on how the technology matures. It also notes total investment in the space exceeding $1 billion as of 2026. That does not mean the commercial future is guaranteed, but it does mean serious capital, serious partners, and serious expectations are now involved. And once Google, Microsoft, and major enterprise customers start leaning in, the conversation changes from interesting science to possible strategic platform. Now, let's talk about the real-world use cases. According to the report, neutral atom systems may be especially well-suited for quantum simulation. This is probably one of the biggest near- and mid-term opportunities. Neutral atoms are naturally good at simulating quantum systems, molecules, materials, lattice models, and many-body physics. That could matter for drug discovery, new catalysts, battery materials, and advanced chemistry. Optimization. Things like route planning, scheduling, portfolio optimization, and supply chain design could benefit from quantum approaches, especially if neutral atom systems continue scaling to larger qubit counts. Quantum machine learning. This remains early, but neutral atoms may be useful for certain variational algorithms, quantum kernel methods, and hybrid machine learning workflows. Quantum networking and security. Because neutral atoms may interface well with photonic systems, they could play a role in future quantum communication, repeaters, and secure network architectures. The important thing here is that neutral atoms don't need to win every category. They just need to become the best platform for a few high-value categories. And if those categories include chemistry, materials, or large-scale optimization, that could be economically massive. The report lays out an ambitious roadmap. Near term, it points to 1,000 to 10,000 qubit systems, improved fidelities, and early error correction capabilities. Midterm, it projects 100,000 plus atom systems, fault-tolerant logical qubits, and more practical algorithms. Long-term, it imagines million atom systems, industrial deployment, and deep integration with classical computing and quantum networking. Now, to be fair, those projections are ambitious. A lot has to go right. Fidelities need to improve, error correction has to become practical, hardware manufacturing has to mature, and the industry still needs to prove large-scale commercial advantage. So, the responsible view is this. Neutral atoms are not guaranteed to dominate quantum computing, but they are absolutely one of the most credible paths forward. And the reason people are excited is simple. The platform already shows strong evidence of scalability, flexibility, and commercial traction, while still having meaningful room to improve. So, what's the big picture? Neutral atom quantum computing may be the dark horse of the quantum race, less hyped than some platforms, but increasingly hard to ignore. It combines the elegance of atomic physics, the control of laser engineering, the promise of large-scale qubit arrays, and a growing commercial ecosystem backed by major players. Its biggest strengths are scalability, long coherence, flexible connectivity, and strategic commercial momentum. Its biggest obstacles are gate speed, 2-qubit fidelity, atom loss, and engineering complexity. And that means the future of neutral atoms will likely be decided by one question. Can this platform improve fast enough to turn today's impressive demonstrations into tomorrow's practical, fault-tolerant machines? If the answer is yes, neutral atoms may become one of the defining technologies of the quantum era. And that's why this field matters. Because the future of computing might not just be built on silicon. It might be built on atoms, suspended in light. If you enjoyed this breakdown, like the video, subscribe, and let me know in the comments, which quantum platform do you think wins the long game? Superconducting, trapped ions, photonics, topological, or neutral atoms?